of a diatomic molecule of a rigid diatomic molecule and we found that the energy of rotation level is equal to, where this B is a rotational constant, and it is I square by 8 pi square I. It is C when we calculate EJ actually. EJ, and EJ is equal to actually this. And this is in centimeter inverse wave number. So this is a wave number actually. And we also found that delta EJ from when J goes to J to J plus 1 is equal to 2 it is what is it equal to? It is B into J plus 1, I think.
Yes, sir. J plus
2B.
1.
It is 2B into J plus 1.
Yes, sir. Twice B J plus 1.
This is the gap difference. So when you draw the spectra, if you draw the spectra like when you observe the molecular spectra, you will observe that if this is the first line, it is J equal to 0. This is J equal to 1, and you will find that this is at 2B. So this gap is 2B. Then the next is at 4B. So this is again, the gap is 2B. Actually, there is an increment of 2B between each two levels. Then you have 6B here. You have 8B here. This is a 12B, 10B, and so this is how the spectra allow transitions between energy levels of a rigid diatomic molecule will look like. Okay, and we also know the selection rule was delta J is plus minus 1. One of the important factors for the origin of this rotational spectra, that means what is the basic condition for a molecule to show the rotational spectra, because every molecule or every linear molecule or non-linear molecule or symmetric molecule or asymmetric molecule will not show us this rotational spectra. And for example, I will tell you that any homonuclear molecule, like for example, that is hydrogen, etc., will not show any rotational spectra. And while as heteronuclear, which are asymmetric, for example HCl, carbon monoxide, these show rotational spectra. The basic difference between these two is that whenever a molecule rotates, for example this, let's suppose it is carbon monoxide, C, I think it should be double bond. Yes, maybe it is double bond, yes. O, this is carbon, this is monoxide, oxygen, for example, or HCl. Here you have HCl. So whenever it rotates, end over end rotations are about a bond axis, and bond axis shows any very least change. They do not show the major change. There is a change in actual change in dipole moment. The dipole moment changes. If initially a molecule has some dipole moment, um, any value of the dipole moment, and when it rotates, this dipole moment will change. Okay, there will be a change because of the rotation of the molecule. The energy is high energy of the molecule, and due to this change, this dipole moment will interact with external field, and this external field is provided in the form of electromagnetic radiations, electromagnetic waves. The energy range in which the rotation of a molecule happens or the rotational spectra can be observed falls in microwave region. It falls in microwave region. And the energy range, that means the wavelength of this microwave, typically falls into, let me give you the value of this energy, microwave length or energy. You can convert the wavelength into this energy and then energy back into wavelength. So that is an easy thing to calculate. So microwave, let me see the value. Yes, here it is, microwave. And microwave has a 1 centimeter to 100 micron, 100 micrometers. This is the range of wavelength, and the frequency is, it is 1. This corresponds to a frequency of 12 hertz to 10 hertz. Okay, and the energy is 10 to 10 is about 3, I think joules. It should be joules. Yes, you can convert this anyway. So I will give the value is 1237 divided by lambda. That is E. You can convert it. Wavelength into energy and energy into wavelength back. This is the expression, simple. So this is all about this rotational spectra of a rigid molecule. Then if we consider the molecule which is not rigid, if we consider a molecule which is not rigid, non-rigid, and most of the molecules are not rigid. In practical, no molecule is rigid. Every molecule is a non-rigid. So what does this non-rigid molecule do? If you have one atom or two, then the rotational spectra of a non-rigid molecule will be dependent on the distance between the two molecules. And now it is not fixed as in the previous case in the rigid molecule. So in this case, it is the distance that R actually, which is not equal to RE, equilibrium. This RE is the equilibrium distance before any rotation. Okay, and that when a molecule rotates at very high speeds, by very high angular velocity or angular frequency, sorry, then the molecule will tend to vibrate because of the very high velocities, high angular speed of the atoms. And there will be a centrifugal force which will be acting on each of the molecule because of the other one, each of the atom because of this one. Okay, so if this rotates, so there will be some, it will try to move towards it, it will try to move away, or sometimes it will try to move inwards, this will try to move outwards. So there will be a vibration or an oscillation. We will study in detail the pure vibrational spectra, vibration, and this vibration occurs, it does not occur by its own, it occurs because of this centrifugal distortion. So there's a distortion in the bond axis actually due to centrifugal forces between the two atoms. And the centrifugal distortion will result in the decrease of the total energy level. That means if an energy level earlier existed at some value, for example, if J equal to 0 is here and J equal to 1, due to centrifugal distortion, there is a decrease. This will go like this. This is when this is non-rigid. So there is a decrease in the rotational energy levels because some of the energies will be taken out by because of that centrifugal distortion. And this centrifugal distortion is given by the contribution, that is EJ for a non-rigid rotor minus D, because this is a higher order term now, it will be square dependence on this centrifugal distortion. And this D is actually nothing but centrifugal distortion coefficient or centrifugal distortion constant. The value of this D is actually given by H cube this is Kc, and remember that this K is nothing but it is actually the force constant, because elasticity of the bond here, this, that K, and this K is equal to 4 pi square omega square c square mu. Mu is the reduced mass, is velocity of this light actually, and omega is the wave number, angular frequency. In terms of angular frequency, these are constants. Okay. This K. Now because since R changes, so here is I. I is equal to mu R square. So it gives us this EJ becomes inversely proportional to R, because now R is not equal to RE, that is fixed. This R varies now. Okay. So EJ becomes directly inversely proportional to R square. And all other quantities are independent of that vibration, because those vibrations will only affect R. And these are simple harmonic in nature. Whenever there are some anharmonic terms in this, then the equation becomes more expanded, this equation. this. If there are n harmonic terms, then there will be Ej will be equal to Bj into j plus 1 minus, because we are now under n harmonic force, so these all terms will be actually, this is like this, minus all the terms will be subtracted from this term, minus higher order terms j into j plus 1 cube plus k j4 into j plus 1 4 dash dash dash. This is minus here, centimeter, and it is bj into j plus 1 minus d, and this is in centimeter. We are in wave numbers, so in centimeter inverse. Okay, and we also know that d is, we know that b value, b and d, so you can write then d is equal to 16 because you know that b is equal to, IC, and d is already, we have written d is equal to, so using these two you can find out this equation. Just do it and let me know if there is any problem. Yeah. Now if you want to see the separation between the two energy levels, rotational energy levels of a molecule which is not a rigid molecule, which is a non-rigid, how you find? Ej plus 1 minus Ej. Okay, then we can write minus d term because of this higher order term, centrifugal distortion. Is it okay? I am putting up the values first, j plus 1, because we are subtracting higher minus from lower. So this is bj to j plus 1. So our stop j, now it is j plus 1, then j plus 1 becomes j plus 2. Similarly for this d term, centrifugal term. And when you solve it, it comes out to b 2b j plus 1. And in this way, putting up j for, and go from j equal to 0 to j equal to 1, then j equal to 1 to j equal to 2. Similarly, you can draw the spectra then, like we did it in earlier cases. Okay, and there's a shift, as I already told you. You can also calculate the this frequency, the wave number omega, from the rotational spectra by knowing this equation, omega bar square is equal to 4b cube divided by d. When d and b are given, you can find omega of the molecule, at which frequency it is vibrating, from this equation here. You can find this when you know this d. These are constants actually. Okay, b and d. So you can find out b omega at which it is rotating. There are other terms, other things in this. I will not go into that detail, but just to inform you that there is an important concept which often comes in the exam, in net exams and all those, that is the effect of isotopic substitution on rotational spectra. What does it mean? It means that if you have a carbon 12 and you are getting its rotational spectra, for example, and you replace this carbon 12 by carbon 13, what will happen to rotational spectra? This, it means this, that when you substitute an isotope of an element, what happens to the rotational spectra? And this is important. I will give you this assignment for all of you to do it, and it is not a big issue. Only 2 steps, less than that. Just see, check it. Okay, what happens when we substitute an isotope? And it is an important concept in the rotational spectra. Then there comes another concept, which is the vibrational one. And the vibrational one, you have already done the physics of a vibrating oscillator, harmonic oscillator. The harmonic oscillator is the simplest example of vibrational molecule, a molecule which is vibrating. Somebody is writing on this board. Remove these here again. Okay. The vibrating diatomic are simply the vibrational spectra of a diatomic molecule. Simple. We know that if we have two atoms like this, for example, they form a stable bond. Okay, and when they are at equilibrium, they have minimum energies. They are at minimum energies. Okay, for example, chlorine molecule, Cl2, hydrogen molecule, any molecule. Since we know that no molecule is perfectly rigid, there is some vibration which is continuously going on in the molecule. Okay, and when two atoms form a bond, they are connected by those bonds, and these bonds are elastic. So we can understand it like we have an atom here, we have another atom. So these two atoms, the bond length here, or E, let us suppose, it squeezes. So it goes like this. Just you can a spring attached at masses at the two ends. So it can come like this. It can go away from like this. Sometimes it happens that this goes in and this goes away. Okay, and okay, so these are the type of motions, vibrational motions, which can happen when there are two atoms. So on one hand, there is a repulsion between the positively charged nuclei of both atoms. That means there is a repulsion between these two nuclei here. And between their negative electron clouds, because there are electrons. On the other hand, there is attraction between the nucleus of one atom and the electron of another atom. These electrons, this nucleus, electrons, nucleus here. These electrons, this nucleus. So there is a balance between these two. And the total energy of whole system is minimized. In this case, when we try to bring these atoms closer to each other, that means squeeze, we have to apply some energy. Or when we pull them apart, we have to apply some energy because they will resist because of their attractive as well as that repulsive forces. Then any this moment, it will change their equilibrium distance. And there is a then force according to Hooke's law. You know that it is minus K or minus R equilibrium. Because when we have a spring, assuming that this bond is a spring which is attached to some mass, and this F is a restoring force. That's why it's negative, because it's opposite to the direction of motion, a restoring force. And if you see energy, it is 1/2 of K x square. X means displacement actually here. And displacement is that if it was earlier, this was our equilibrium, and there's a vibration, this molecule moves here, this molecule moves here, then there is a change, this is R now. So how much is the displacement from their mean positions? That means this is the displacement from the mean position, this is the displacement from the mean position. That is how we calculate R minus that displacement, which is R minus R equilibrium. And it is 1/2 kx square actually from that Hooke's law. This is also model of simple harmonic motion, simple harmonic oscillator model. Now similarly, if we take any molecule which was earlier at some minimum energy, E1, and we gave it energy such that it vibrates and attains some energy, E2. Okay, so there's a change in the energy because of this vibration, and it vibrates at an frequency omega, oscillating frequency. It vibrates at this frequency omega, which is called omega oscillation. Then omega oscillation will be equal to, we know that, what is that? Mu actually is K by M, so M is here reduced mass, so M goes to mu, reduced mass. Or we can write omega oscillation, this wave number. There's a C in the denominator. Sorry, to centimeter inverse. And again, the vibrational energy EV for a simple harmonic oscillator, what is it? This has been done. You all know it. For a simple harmonic oscillator, we are considering the harmonic vibrations. We are not going to enharmonic. That means there is a this. So it vibrates with this with respect to this mean position. Here is the mean position. So it can vibrate with respect to this mean position to this side or to this side. Similarly for this, to this side or to this side. Since it is a reduced mass, we have center of gravity. So we assume this molecule to be this. And if this is it is mean position, so it can go here or here. And for a simple harmonic oscillator, the energy is given by this expression nu plus 1 by 2 h cut omega. And you know the 0 point energy. When nu is a vibrational quantum number, and this goes to 0, 1, 2, 3. This is a quantum mechanical effect, which is not this explained by classical mechanics, which gives the energy h cut omega only. But from quantum mechanics, we got this nu, and when nu is 0, you still got some energy, that is 1 by 2 h cut omega oscillations, and this is the 0 point energy of a harmonic oscillator. So even when we don't give some energy to vibrate, at ground state there is some vibration energy that is given by this expression. And if you find this ev in terms of the wave numbers, where this omega oscillation is equal to sorry, omega by hc. This here is this hc. I am dividing this hc on this side in this expression. Sorry, here. And this energy is in where energy, so it is in joules. So this is not in joules, this is in centimeter, because we are taking the wave number now. Divided by SC, it is wave number. So this is for nu equal to 0, we will get E0, which is 1 by 2 megabar oscillations. And if you want to find energy, E0, that is 1 by 2 h cut omega oscillation. This is in joules. So there's a difference between these two expressions. Where nu is, we have taken in omega in centimeter inverse, this omega is in centimeter inverse, here omega is in joules. In this case, there omega is in centimeter inverse. So we know that from the earlier knowledge, as well as in this case, diatomic molecule or any molecule can never have a zero vibrational energy. The atoms can never be completely at rest related to each other. This is important result of this expression. And the energy which we are rating here, these two, this is the 0 point energy, and it depends upon that frequency, classical vibrational frequency omega. That is a classical frequency actually. And the selection rule for this, everywhere when you change the nu, for example, this was nu equal to 0. When we have nu equal to 1, what we will get? 1 plus 1 by 2 h cut omega oscillations, that is 3 by 2 h cut omega oscillations. When we go nu equal to 2, it is 5 by 2 h cut omega oscillations. Similar to 3, it is 7 by 2, 9 by 2, 11 by 2. Everywhere we have a ground state, that is 1 by 2 h cut omega. Then we go to 3 by 2 h cut omega. What is the change? That is 1. There's a change of 1 unit in every step, every energy level. And how we draw the energy level, this energy and energy versus distance. wait, sorry, it's a parabola. This E equal to 1 by 2 kx square parabola. This is E here, this is R or X displacement actually. Here in our case X is actually, sorry, X is R minus RE X square. So this is R here, what is the displacement, and this is here R equilibrium. If we plot the energy diagram of a simple harmonic oscillator or simply a vibrating molecule, and it is just resembles with that simple harmonic oscillator, which is a parabola actually. I'm not
सर हमने यही से बोला सर हम पूरा सिलेबस पढ़ेंगे मगर एग्जामिनेशन 20 दिसंबर से स्टार्ट
हाँ यूनुस
इन
यूनुस
लोगों ने माना नहीं.
Okay, no problem, let us, we will discuss it later. Okay, no issue. You discuss with you, आप ग्रुप में डिस्कस करो कब तक क्लासेस देनी है, मुझे बता दो. I don't have any problem.
ओके सर ठीक है.
यूनुस चेक आते ना साफ है वहाँ बस है वहाँ करो पगा बाकी. आपकी आवाज कट रही है. Okay, so the energy diagram for a vibrating molecule or a simple harmonic oscillator, this is the R equilibrium here, and if we take E vibrational here, and this is in centimeter inverse units, that means you are converting the wave number frequency into wave number, and this is R here at different nu, that means changing the vibrational quantum number. For the nu equal to 0, this is the 0 point energy, so it is not 0 actually from quantum mechanical considerations. Then this is nu equal to 1, nu equal to 2, nu equal to 3, nu equal to 4. So this separation is everywhere equal. The separation is equal actually. Okay, and this is the internuclear distance actually here between the two nuclei. Okay, and if you convert, sorry, if you calculate the energy level from, sorry, it's not now J, it is nu, E nu, it is vibrational quantum number, not the frequency nu. Remember that. So it is vibration quantum number. If you go from nu plus 1 to nu, if there is a transition from upper level to lower or lower to upper, what you will find, it is nu plus 1 by 2 omega oscillations in terms of wave number minus this is nu plus 1 by 2 omega oscillation. So then if you solve it, it comes out to be omega oscillation. So this gap, this is omega oscillation here, omega bar oscillation, and it's everywhere equal, it is same everywhere. Here this gap is also omega oscillation. There's a difference between now the vibration and the rotational. There it is unequal, this 2b, the gap comes 2b and it increases. Here it is omega oscillation, the vibrating frequency, and you can write then wave number, that is called spectroscopic wave number. This wave number in the terms of spectroscopy, it is E, sorry, centimeter inverse. Okay, this is the vibration spectra for a harmonic oscillator actually. So that means we are not considering any centrifugal distortion, or we are not considering any anharmonic effects in this case. But when we consider the anharmonic effects, the spectra will have change, actually it will change. And I will leave it here. Let us discuss it tomorrow. Okay?
Yes sir.
And just check it and let me know if there is any problem, because these are simple and calculated questions. There is nothing extra or nothing that much of physics which you don't know. Everything is there that you know.